So the title is Modeling Focus Beam Propagation in Scattering Media, and these are my learning objectives. Teaching objectives. Yes, you will learn focus beam distortions in scattering media and the need of focus beam computational models. And you will understand the concept, equations and principles applied in focus beam propagation. You will learn plane wave propagation in scattering media. That is the basic wave propagation in scattering media. And after that, we'll learn Huygens-Fresnel principle. Then we will use that Huygens-Fresnel principle to develop a focus beam propagation models. You'll learn that at the end. You already know about this focus dot, why it gets this kind of a shape. So in a non-scattering medium, when we have a plane wave, it hit on this lens and then refracted and propagate to the nominal focal point. And then it propagate this way, and you can detect that signal in that side also. In a scattering medium, you will have scatterers. Because of these scatterers, this beam is getting distorted. This distortion propagate, and it will decrease the amplitude or attenuate the amplitude, blur the signal. So this is a problem in optical microscopy. So what we plan to do is to do a model so that we can get a better understanding of microscopy. But this is a difficult problem. See, I picked this one from Eric's lecture. In this one, this area you can get a clear image. This is a nonlinear optical microscopy. You can get a clear image here, but as you go deeper and deeper, it is getting blurred. So if we can understand what's happening in focus beam propagation, when scatterers are present, then we can model this kind of thing, and that kind of information will help us to develop or design methods to mitigate scattering. And also we can think about designing better illumination or detection schemes, so we can get more information. We can get more information from microscopic images. And recently developed an experimental technique about 5-6 years ago. In that one, what they did was they illuminated from this side, and they put a detector here, and they change the beam profile on that side until they get a good intensity on the other side. That means they change the beam profile so they can get high intensity at this level. So they manipulate the scattering to get high intensity. So in that experiment, they didn't know anything about what's inside. They didn't know what, it is like a black box. So they modulate the incident light and get high intensity. But if you know this information, how these what's happening inside the tissue, how this focus beam is scattered by different scatterers, then they can combine that information and develop better illumination and detection schemes. Biological tissues are complex, and these scatterers have different shapes. They are oriented in different directions. They have different refractive index. So modeling this one is really complex. It's a hard problem, but we can simplify the problem. We can consider only two layers, dermis and epidermis, and we can assign. We can, let's say we know all the optical properties, and we know layer thickness, and then we can do a simulation, but still. We have a problem of finding this distortion because predicting this distortion, because we don't know how this focus beam how this focus beam is going to affected by these scatterers. So I have three cases. In this case, the epidermis have high scatterers. That means scattering coefficient is high, and dermis has a low scatterers. Well, let's assume that. And in this case, I inverted the sample. So the dermis is right here and the epidermis is there. And this third case, I mixed up these scatterers. So we have these kind of three cases. And we want to model this one. But before modeling, we want to get an idea what kind of a distortion we are going to get. Can anyone speculate any ideas what kind of a distortion we are going to get? Are we going to get maximum distortion in this one, A, B, or C? So I also can speculate some ideas. So for case A, we have large scatterers there. So the focus beam is propagating and hitting these large scatterers. When you have large scatterers, their scattering field is high. So it's going to distort here more. And so when it reaches this limit, it's going to distort further, and you may get a largely distorted signal at this point. And I can also speculate another idea. I can say, okay, in this case, we have large scatterers at this location. These scatterers are small scatterers, so the scattering is low in this region. And when we come to this region, the intensity is high because this is focal volume, and that high intensity of incident might create a high scattered field. That scattered field might distort more. So we may get highest distortion at this location from this case. So we don't know whether this one will give the highest distortion or that one, but we can speculate some ideas. And in this case, we can mix these samples, but the thickness is bigger in this sample. So we can say, so the larger scatterers are spread all over the tissue. We might get a maximum distortion in this case, but we don't know. So even we have this kind of simpler case, not a biological tissue with all the components. We just assume smaller and larger scatterers for these two layers. Even for this simple problem, we cannot predict what's happening at the focal point in focal volume, whether we get large distortions or not. So what I plan to do is I'm going to pose a single scatter problem. So this is what we started. We started this problem about 2-3 years ago. And this problem is well defined. So here we have a plane wave incident, X-polarized plane wave incident hitting on a lens. We consider this lens as a planatic lens. That means it's a perfect lens. It will not provide any distortions. And then focus beam is propagating toward the nominal focal point. And we put a single spherical scatterer. And here I put an XY plane detector. This is not a physical detector. This is like we put an XY plane detector so that we can capture what's happening in this plane. And here's the nominal focal point. So we define this single scatter problem, and we are trying to develop a model to get the solution for this simple single scatter problem. And you are going to do this lab during this afternoon and try to find the answer. So in my lecture, I show the technique we use to develop that model. So when you have a problem, first we look at existing technique. So first technique is FDTD solution for Maxwell's equation. FDTD means finite difference time domain solution, and it solves Maxwell's equation rigorously in a voxelized space. So when I had that problem initially, we collaborated with Professor Andy Dunn at UT Austin, and we asked them to do the simulation because we are developing a new model here. We want to compare our results with them. So we gave that problem to them and asked them to simulate that one. So they simulated that one, and for that simulation, time was like 300 process hours. But they use supercomputers with 48 cores, so they can get results in 6 hours. Still, the time is like 6 hours. But this is a simple problem, but why we need that amount of time? Because in FDTD, we solve Maxwell's equation. When you solve Maxwell's equation, you have to solve step by step. You have to, solve one voxel and go to next step, next voxel. Voxel by voxel, you have to solve that one. So you need enormous computational resources for this one, and also the size of the voxel has to be small, because if you make bigger voxels, then you get errors. So you have to make this voxel size as small as lambda by 20, so the wavelength by 20. For our case, they use lambda by 30 to get better results. And other than that, you have to define this boundary with absorbing layer, because when this wave is propagating inside the voxel, when it's come to the boundary, it's going to provide artifacts, because now the wave comes to the boundary and you have to go somewhere. So you have to put an absorbing layer there to absorb that one. But still there are some artifacts, so they need to define this volume as big as possible and also to get a good results without errors. So they defined 16 by 16 by 16 micron volume to do the simulation. And other thing is, when you have to define spheres, there are some staircase errors, because these spheres are defined with voxels. And so you can see this kind of a staircase errors, and that will provide some kind of a error. So to minimize that one, you need to have small voxels. That's why this computational cost is very high for FDTD. And other approach is Monte Carlo simulation. In Monte Carlo simulation, you can start propagating photons from this area toward the focal point and do the simulation, regular Monte Carlo simulation. In earlier cases, they did a regular Monte Carlo simulation. They did not consider the wave nature of light. So we didn't have a diffraction or interference effect in this area. So those results are not that accurate, for small volumes. Like when you consider microscopy, we are talking about 200, 300 microns max. So for that volume, they are not accurate. And in later models, when photons are propagated, the photons get the vector nature. So you include the electric field to the photon and then propagate in later models. But still, this sample contain randomly distributed scatterers, so that provides mean behavior. Still, if we define the particle at a specific location, this type of system require a large number of photons. That means you need a lot of time. So these models consumes a lot of time. And if we use this kind of a model to get results for that kind of a simple problem, if you do the simulation today, you need to wait some time to get the results. Probably for this afternoon lab, if you do it today, probably you need to come back tomorrow to see the results. If you want to do some changes, you need to do all the simulations and set up that one, and tomorrow come back and see the results. But so we are thinking about a faster model, a model that can give results quickly. So our actual problem is this, and we know this thing. When focus beam propagate to the nominal focal point, we can decompose that one into plane waves. So we have that information. So now we are thinking how we can include that information into this actual problem. But before that, it's better to understand how plane waves incident on spherical scatterers. So if we know this problem, if we know the answer to this problem, then that may be helpful to solve this focus beam modeling problem. So to learn that one, we have to go through this key concept, equation and properties. There are a lot of math in this area. So, but still I'm going to talk about that one. So you'll get basic understanding about electromagnetic wave, Maxwell's equation, plane wave propagation, and me solution to Maxwell's equation, that means plane wave incident on spherical scatterers. Let's go through those key concept, equations and properties we need to learn to do this modeling. So the first thing is light is an electromagnetic wave. So in this one, this electromagnetic wave has an amplitude, and electric field is this red one, and the magnetic field is blue one. They are orthogonal, and their propagation direction is orthogonal to electric and magnetic field. Peak to peak distance is lambda, that's the wavelength. And for this electric field, we can write a simple equation like E naught sine function. So this provides the sinusoidal function, and kz minus omega t. Kz is this direction, omega t is the time component, and this is the angular frequency. But we can write that equation in a different way so that we can include the phase information. So in this equation, I put the axis here so that we can write cos plus sine, cos plus I sine theta type equation, cos theta plus I sine theta type equation. So this is cos kz minus omega t plus I sine kz minus omega t. E naught is the amplitude, and the phase is given by this factor. When we write this equation in that format, the phase can be calculated by imaginary part divided by real part. That's why we use this format. So when we use this format, we can calculate phase at any given location, and then we have that information for our modeling. That's why we use this format. So in Euler's formula, we can simplify that one. E naught equals exponential I phi. The intensity of this electromagnetic wave is given by this equation, half the real part of electric field times magnetic field, and it is proportional to amplitude squared. So the E naught is this maximum amplitude. So we can use electric field for our modeling. So this intensity is proportional to E naught squared. So do you have any questions about this electromagnetic wave? Okay. So now we go to Maxwell's equation. So we know electromagnetic wave contain an electric component and magnetic component. These Maxwell equations provide exact model for electromagnetic wave propagation. And it provides theoretical foundation of optics, and Maxwell's equation models wave interference, diffraction, and polarization. Let's look at this Maxwell's equation, four Maxwell's equation. Sorry. In this one, it says when there is a change in magnetic field, it provides an electric field, it generates electric field. And the second one says when there is a change of electric field, that creates a magnetic field. In addition, current also generates a magnetic field. This third law says when you take an enclosed surface, this net electric field is given by the charge density. And the fourth one is in an enclosed surface, net magnetic field is 0 because you have a magnetic line going and come back to the magnet, so the net magnetic field is 0. We can consider the free space. When you consider free space, there are no flow of current. So this equations, we can rewrite this equation like that. And there are no free charges in free space. We can rewrite this equation like that. Now we can have some relationship in this one where E and H, here H and E. So we have some similarities in this equation. That's why in FTDD, when you solve that one, you need to solve, if you have H, you need to solve E and get that E and apply it there, find the H. You need to run step by step. You cannot go from here to there directly, because you have to solve one step at a time and move forward. That's why solving Maxwell's equation takes time. So that's why it is limited for small spaces, even though we can we can apply that one for large scales. But because of this solution technique, there are some practical limitations. I mean, it takes years to solve if you take like a mile by mile, like a big area. It takes years to solve that kind of thing. So we can take those two equations and then we can substitute one or other and then can generate this wave equation in free space. In this equation, C is the speed of light in vacuum, and when second derivative of electric field in time is equal to a second derivative of electric field in space. So the time variant in is equal to the space variant. So this is given in wave equation in free space. What is the solution to a wave equation? So the general form is it's a function of r minus ct. This r is the position vector. It shows the direction of propagation, and r minus ct. And we have a plane wave solution. We can write in this form. Once you substitute this quantity over there, it will solve this wave equation. So this is the plane wave solution. You can simplify it and write like this. The k is the wave number, omega is the angular frequency. And plane waves, we draw plane waves like that. And the phase is given in that way. We can select one phase. Let's say phase angle equal to 0 or 180. And when we join all these phases together, we can generate one plane. So here we take one phase at different distances. So this kind of a representation is called wave front. So here we show a wave front. Now we are going to consider polarization. Polarization is described by specifying orientation of the electric field. So the electric field, when it propagates, it is oscillating up and down, or depending on the direction, it's oscillating. In this case, it is oscillating along x-axis. And we can calculate parallel and perpendicular component of the electric field. In this case, we have to find the incident field. We find incident field like that. Let's say there's a mirror here. So we have the wave and it propagates and hit the mirror and goes in that direction. So now you have a normal which is coming out. The incident wave and normal, it's lying on a plane. That is the incident plane. That's how we get the incident plane. So depending on the incident plane, we define parallel and perpendicular component. So in this case, if we consider xz as our incident plane, then this electric field is parallel. It's parallel to that plane, xz plane. But we can consider this one as, if our incident plane is this one, yz plane, this plane, then this electric field is perpendicular. So that's how we get the parallel and perpendicular planes in polarization. But here we are looking like this. But someone can look at like that, but still wave is propagating vertically. But when you look at that, for that direction, you need to get the projection of the electric field. For example, now this wave comes and hits on a scatterer, and then it creates a three-dimensional scattering field. But we want to consider this direction, W direction, and then the orthogonal axes are U and V. We need to find how these polarization contribute to this U and V. To do this, we need to project that one to U and V. In this case, Ex equals E naught exponential ikz, Ey equals 0, so we use that same case here. Using that, you can project that one to EU and EV. So those things are important in modeling, because you have, when you do modeling, you don't have same exact polarization at all locations. It's when we look at that scattering field, when it is going in one direction, you need to look at how this polarization is going to contribute to that direction. So, this is an important concept. Okay. So do you have questions up to here? This wave basics, Maxwell's equations, polarization, plane wave propagation. Do you have any questions up here? Okay, let's go to next topic. Me solution to Maxwell's equation. This one is an analytic solution to Maxwell equation in spherical geometry for an incident plane wave. So originally this was formulated for incident plane wave, but there are some other variations. So for that one, we have different variations. We have spherical waves coming in and hitting this one, but original me theory was defined for a plane wave. And it described electromagnetic waves scattering by a sphere. The solution is an infinite series, but it converges. It provides both internal and external scattering field. It provides internal field, external field at any given location. What they did was they considered the boundary condition, the internal field plus external field equal to the incident field at the boundary, then find a solution, they found the coefficient and found the solution for internal and external fields.
So Jonica, I have a question. Could you go back 2 slides where you lost one more? So I have a question about this. So you have an incident, you're depicting an incident wave onto a scatterer, and then you're, I think, selecting a direction W for the propagation of the
Scattered field.
Okay.
Yeah.
But of course, in reality, the scattered field goes in all directions, but you're selecting this one direction and you want to depict potentially the polarization state of that scattered wave. And so the question is, it sounds as though the polarization state of that scattered wave is simply determined by a geometrical transformation from one coordinate system to another. And so I guess my question is this, so there's no intrinsic change in polarization. Is there no intrinsic change of polarization imparted due to the interaction of the wave with the particle? Is it simply geometric? Meaning that if you selected a scattering direction in the same direction as the incident wave, would the polarization of the scattered wave in the same direction as the incident wave be identical with each other?
Yeah, if you consider z direction, it's going to be identical. But imagine this way, at this location, so the bottom of the scatterer, this plane wave hits and its polarization is along x direction. So now this scatterer sees as that polarization. So that polarization comes in and hit this spherical wave. So it sees that one. But when you consider the scattering, scattered field going in one direction, it gets the projection of that polarization. It's
okay, so I think I understand. So basically it is simply a geometric transformation.
Because okay, nothing is going to happen at that location.
Right. So the other question I have is that I think there was a question earlier in kind of the free time about, so that characterizes the polarization state of the scattered wave. The polarization state of the scattered wave is purely a geometric transformation of the incident wave into the direction of the scattered wave that you're considering. Now, when it comes to amplitude and phase, that is not geometric solely, right? That is due to the interaction of the incident wave and, in some sense, a re-emission. And that affects amplitude and phase in a way that cannot just be determined by the geometry. Is that correct?
That's correct.
Okay.
Because what's happening is when this field incident on this particle, the atoms are going to vibrate. So then it generates dipole. If particle is bigger, there are multiple dipoles. And so those dipoles, generation of those dipoles decide the amplitude and phase. So the propagation of those dipoles.
Are there any other questions?
Okay, so during afternoon lab session, one exercise is about this me simulator. So let me explain a little bit about these panels. This one gives sphere data. We have two distributions, monodisperse and polydisperse. In monodisperse, you need to give the diameter and concentration. And then this panel shows a sphere refractive index and medium refractive index. And you can use the wavelength with steps 5 or 1 or whatever, you can use different choices. And then plot scale, linear or log for these plots. Here's a scattering cross-section. You can calculate scattering cross-section. You have seen equations yesterday. Using scattering efficiency. Me solution calculate the scattering efficiency, then we calculate the scattering cross-section. Here, me solution provide the phase function. Based on that one, we can calculate the average cosine of phase function, that we call it as G. And when you have scattering cross-section, you can multiply by number density and calculate the scattering coefficient. When you have scattering coefficient and G, you can get the reduced scattering coefficient. That's how we build this tool. So we use me theory to calculate the scattering efficiency and phase function. and then use that data to generate this scattering cross-section, reduce scattering coefficient G, and we define number density depending on concentration. This is the number density for 1 cubic volume. And just one nice one. So you'll see this kind of a plot, and there are some exercises you can do those exercises. I'm going to talk about this phase function for Rayleigh scattering. Okay, so here's the Rayleigh limit of mean scattering. That means wavelength is much bigger than the particle diameter. And Eric also mentioned this one, dipole radiation. So when particle is so small, we have a single dipole, and it's a Hertzian dipole. It generate electric field like that. When you consider far field, it's going to be a donut. So it provide this kind of a donut shape. And this is our polarization axis. So it oscillates along the x-axis. And when it propagates toward the center, this is where the scatter is, it is oscillating in this direction and create this kind of a donut shape profile. And then in parallel polarization, what we did is we get XZ plane, this plane, XZ plane. So we get this cross section, and you will see two circles in parallel polarization. In perpendicular polarization, the polarization is along that direction to our considering plane. We are considering XZ plane. So this is perpendicular to XZ plane, and it still create this kind of a donut shape, but we are looking at the cross section in XZ plane. So this gives you a circle. So that's why you get this type of different shapes for parallel and perpendicular polarization. Do you have any questions about this one? I think yesterday someone had a question. Yes, so this is the Rayleigh limit of mean scattering. Okay, now we go back to our original problem. So the original problem is we have single scatterer, focus beam is propagating and hitting that scatterer, so we want to model that one. And we decide to look at the plane wave incident on spherical scatterer. So let's look at this case in detail. Here we have a detector, and we want to see what kind of a scattered field coming into this location, because in this detector what we do is we define a grid, and we want to look at what's coming into each grid, what kind of a scattered field coming into each grid. So we implement this one mathematical like that. So this is the X incident, X polarized incident, E inc, and then this incident field hit on the spherical scatterer, then it create a three-dimensional scattered field. But let's say we consider one direction, this direction, and that create an angle with z-axis theta, and then this plane has an azimuthal angle of phi. It's a typical scattering problem. So now we will get two components, two other for the scattering field, perpendicular scattering field and parallel scattering field. Let's consider this distance is r. Then it is given by this type of two equations. Let's look at this equation in detail. This part is the incident polarization component projection, this part. And then S2 r theta is the amplitude scattering matrix component. Look at this S2 r theta. This is r dependent. That means it is distance dependent. So this is not the far field solution you normally see in books, because in most of the books they use the Mie theory and get the far field solution, but in this case it is different. This calculation is a little bit complex than normal calculation. So this is distance dependent amplitude. And then exponential IKR, this I times phi, this is the phase. This provides the phase from this point to other point. And this S2 is a complex value. That means it contains a phase. And then this scattered field is a spherical field. It starts to propagate from center to outward. So it's a spherical field intensity decrease with the distance. So we have this KR part. That's how we get the scattering field at a given distance. Same thing for perpendicular field. We get the S1, so that amplitude is different. This is what we get from Mie theory. And we can calculate the scattering component, scattering field component, perpendicular and parallel component at a given location. In the far field, it is much simpler. It does not depend on R. This is what you normally see. So you don't have R dependent here. And beyond certain limit, we can use this these equations to get the scattered field at a given location. How we define far field, it's actually complex. For each particle, this far field is going to be different. It depends on the refractive index and wavelength. So normally, rule of thumb is beyond 10 times of diameter, up to 4 micron particles, beyond 10 micron diameter, 10 times of diameter, we can consider it as a far field. In Mie theory, this is how Mie theory calculate S1, S2. I just want to show this equation. These are complex equation. In this one, this limit is infinity, but we find a limit. Beyond that limit, the errors are so small, so we don't need to calculate all the coefficient to calculate S1, S2. And these are the Mie coefficient A and B, and they can be calculated using Riccardi-Bessel's function. So all these things are inside that Mie simulator GUI tool. You use these equations to calculate S1, S2. Now, plane wave incident on this scatterer. At this point, we have the scattered field, but incident field is also coming along this line, and so we have incident field also. So the total electric field at this location is a summation of incident electric field and scattered electric field. Now you can see these electric fields are represented by vectors. Now this vector is directed this way and the other one is directed that way, and this incident vector is directed another direction. And anyone tell me how to sum these vectors? Electrical engineers. How do you do it? When you have vectors with different directions, what is the easiest way to sum them? Yeah.
I was thinking vectors, you can sum them up in k-space. The k-space direction of propagation. Or
Yeah, but Yeah, that means you project everything into one direction, this direction of propagation. Yeah, it's an answer. But imagine we don't consider only this one. We have the next neighboring location. So in that one, the propagation direction is a different direction. So the, it has a different propagation direction. So when you represent those things in a plot, it's very hard because one has one direction, other one has another direction. So the best way is, I think there's a hint here, this axis. So you project these vectors into x, y, and z directions. So that is a common and easiest way. So you have I, j, k vectors. I vector is along x, j vector is along y, k vector is along z direction. So you project these vectors into x, y, z directions, and then you will have components called x component, y component, and z component. So you can get x, y, z component, and now we are in a common frame. So we can, when we calculate the scattering field at a different location, we calculate Ex. So you can show Ex only in one image, Ey only in another image, Ez in another image. So this is the easiest way. There may be other technique, but I found this one is the easiest one. But imagine these electric field components are not real numbers. They are complex numbers. They carry phase. So you have to do complex number addition here. These are complex numbers. You need to do complex number addition. And how do you do complex number addition? So you have a real part and imaginary part for a complex number. How do you do complex number addition?
You add the real part and imaginary part.
Separately. You get the real part, you add the real part separately, imaginary part separately. Yeah. Okay. Now we go beyond one scatter. We look at two scatter problem. So now, so we want to finish this plane wave incident for different cases, and then we go back to focus beam. So here we have the detector. We have two scatterers. And when you have two scatterers, we can write this equation. This is the superposition theorem. The electric field at this location is given by incident field plus summation of scattered field of each scatterer. This ns is a number of scatterers. In this case, it is 2. Sorry, this should be A. I forgot to change. So this is the electric field at A, and ns is number of scatterers. Now, we have these two scatter case. It is not a simple case because what's happening is we have primary scattering. That means we have a scattering field from the scatterer, and that scattering field effect on this detector, and we can calculate that one. And this one has a scattered field, and we can calculate that one. But after that, now this one provides a three-dimensional scattered field. So this is going to hit the first scatterer, and then it will generate another field. So it will generate a secondary scattered field. And the same thing, here the first scatterer provides a scattered field, and it affects the second one, and it generates another scattered field. You can go on like secondary scattering, tertiary scattering. But the thing is, this scattered field is a spherical wave. So when you have a spherical wave, that intensity decreases with the distance. So the effect is going to be smaller and smaller. And for cases we consider, like for 5 micron scatterers, I found when they are like 1 micron away, the secondary scattering is like 4 orders smaller than the primary scattering. So the tertiary scattering is much smaller, like 7-8 orders are smaller than primary scattering. So we can only consider primary and secondary scattering for certain cases. But depending on the scatter size, if scatters are too big, we may have to consider tertiary scattering. Currently, we think considering these two may be enough to get an accurate result. We have multiple scatterers, so they will provide this kind of a multiple three-dimensional scattering field. Given at any given location, you do the same thing as for two scatterers. You can calculate the scattered field from each scatterer and calculate the total field in the detector. So there's the same principle applied for multiple scattering. So now we know a lot of things about plane wave incident on a spherical scatterer. Can we solve this problem using this information? I think we discussed plane wave propagation, but we didn't look at the focus beam propagation. So now we need to look at the focus beam propagation. So here we have plane waves incident on the lens, and then it create a convergent spherical beam and propagate to the nominal focal point. This kind of a lens, this is a planatic lens, that means perfect lens. We can represent that kind of a lens with a spherical cap like that. And then waves are generated from the surface, inner surface of that spherical cap. So that's a representation of lens geometrically. And then this incident light, expolarized light, the polarization is along that direction, and when it comes to this location, we consider parallel and perpendicular component, and for these components we have to calculate the projection of this incident vector. Now at this case, E perpendicular, which is 90 degrees perpendicular to E incident, is going to be 0, and E parallel is going to be E incident. And at this location, E parallel is going to be 0 because it is along y-axis, and E perpendicular is going to be negative E incident because it is directed in that direction, other direction, towards the board. So now the thing is, we need to calculate all the electric field polarization along on the surface of this spherical cap to do the modeling. And this incident, we use flat beam. Flat beam means the intensity is considered as a constant. We consider it as 1. So the whole intensity is going to be 1 here. And then we have our E naught is 1. And we have this E theta phi distributed in this spherical cap. And let's see how we do in analytical solution. The energy is coming from this side, and then energy pass through this lens. So energy incident on the lens is equal to the energy that exits. We can use this relationship. This is the electric field at the surface, the magnitude of the electric field. This is the incident electric field. N1 is the refractive index on incident side of the lens, and M is the refractive index of the medium. So we can calculate the electric field, the value of electric field at this surface, inner surface of this spherical cap. Then we have to calculate this polarization, parallel and perpendicular polarization. If you recall that cos phi, sin phi calculation, when we looking at the polarization at different direction, we can use that equations to calculate parallel and perpendicular component. So these are the parallel and perpendicular component of the incident electric field on the curved surface, this spherical surface. Then we do integration. So we what we do here is we calculate the electric field at rho phi z. Let's consider rho is the distance from optical axis this way. Let's say rho is here. Then phi is the azimuthal angle around this z-axis, and z is distance from this nominal focal point to our interested location. So we are going to calculate electric field at that given location. That's how we calculate, mathematically calculate that kind of a cigar shape figure, cigar shape, the intensity distribution. If you look at this one, what they did was they integrate the whole 2 phi and theta max. Theta max is this one, this is theta max. The whole area of this spherical surface, this is E theta phi, that electric field is integrated, and so that provides the electric field at a given location. So let's look at this one. This is exponential I times something. So that means it gives a phase. This provides the phase. So this phase is relative to this focal point. And E phi is this value. We can substitute that value. And then this exponential part provides the phase at the focal point with respect to length. So the phase propagation from here to there is given by this one. So Kf, this is the propagation phase. So what you get here is phase at our given r phi z, rho phi z location in this equation. You do the integration, you get the results. That's how we do in analytical equation. And do you have any questions up to this thing? This is the analytical solution. This was developed about 60 years ago, 1959. And so you define the electric field here, and then you calculate the location you are interested in, and then integrate everything. So that's basically what they have done. Okay, in numerical aperture, you have a larger numerical aperture like this one. When you have a larger numerical aperture, it's going to provide a tighter focus like this. And when you have a smaller numerical aperture, you can reach, your probing depth is larger, but the resolution is not good in this case. But when you have a larger numerical aperture, you can get a better resolution. So there's a compromise in that. And we need to include this numerical aperture because the numerical aperture define the size of this spherical cap. If numerical aperture is 1 means in, let's consider the medium is air. If numerical aperture is 1, that means this size of this one is going to be hemisphere. It's going to be hemisphere, that we consider that total hemisphere. But if numerical aperture is small, then it's going to be a small, depending on that theta max. So now we know this thing. We know analytical solution to focus beam propagation, and we want to solve this problem. But still there's some missing part, because in this analytical equation we consider this whole electric field, and you do the integration. You cannot separate that, and you cannot find the different plane waves, because we are thinking of using plane waves for this focus beam. But in analytical solution, you get the full complete integration, but you cannot separate that one. So we need to think, find another way of doing this one. So here comes the Huygens-Fresnel principle. According to Huygens-Fresnel principle, each point of an advancing wavefront acts as a source of outgoing secondary spherical wave. So what it says is you can get any location of the wavefront and then consider that one as a spherical wave propagate from that location. So here I consider two locations. This is a plane wave. So this is the spherical wave, and these spherical waves will constructively and destructively interfere and provide a plane wave again. So the destructive interference cancels out, and finally it ends up with another plane wave. So every time when you use this Huygens-Fresnel principle, like in this example, you have this kind of a wavelet propagating like this, and another wavelet propagating like that. They have different phases at this location, and depending on their phases, they will constructively interfere or destructively interfere or cancels out, and finally end up with a plane wave. Same thing we can apply for focus beam. In focus beam, we have a wavefront. We can consider a single point and apply Huygens-Fresnel principle. Now we can, now in this place, we have a wavelet going in that direction, and here wavelet goes in another direction. Then we can get the vector addition of those two wavelets and get that amplitude. And if you do that one for this wavelet at this spherical cap, then all other vectors will cancel out and finally end up with another spherical cap at this location. So we are going to use this Huygens-Fresnel wavelet in focus beam modeling. Here the area disk radius, this is how you see focus beam in XY plane. If you have a focus beam is coming from bottom, if you look at the XY plane, this is what you see. You will see these things in your lab. This is the Huygens-Fresnel wavelet, and when you consider M-1, its phase, and this one will have the same phase, because from this spherical cap, from this focal point to spherical cap distance is constant. It's a focal length. So all these wavelets travel same distance, so their phases are going to be the same, and then when you add them together, that provides constructive interference. In this case, we'll have a destructive interference at this location. You can see in M-1, it is propagating like that, and it provides a positive phase at this point, and this M0 propagate and it has a negative phase. When you add these two together, that provide destructive interference, and you will see minimum or zeros at these locations. So this is everything, as Eric said, depending on constructive and destructive interference, this wave summation. So now we can look at how we implement this Huygens-Fresnel principle in a non-scattering medium. So first we consider in a medium without any scatterers. What we did was we need to sample this spherical cap, because we want to generate as many Huygens-Fresnel wavelets as possible from this surface. If you increase number of Huygens-Fresnel wavelets radiating from this surface, the results are going to be much better, because when you have few radiating points, the vectors have to cancel each other. So if they are if one is like that, other one has to be like in the same opposite direction to cancel out. But now if they are not, then we don't get a very good result. So what we do is we uniformly distributed points on this spherical cap and then generate Huygens-Fresnel wavelets. And here's our detector. We can put a XZ plane detector or XY plane detector, and we calculate the electric field at a given pixel, given location, given detector grid, project wavelets from each radiating source to a detector point, and phase advances with traveling distance. So here we have one type of phase. So we can set this phase to 0 all over the surface of the spherical cap. And when this wavelet propagate, this phase advance, and it advances with k times dj. So if this distance is dj, that is the advance phase. So what we get at this location is E naught exponential I times this phase. And these vectors are coming from different directions. They have so they are directed in different ways. We have to do the vector addition here. So to do the vector addition, what we did was we get the Ex, Ey, and Ez components separately and add them together. So in your tutorial, you will see Ex, Ey, Ez. Because we did vector addition, that's why you see Ex, Ey, Ez. And this is X-polarized light. Ex component is the dominant component. When you have a smaller numerical aperture, you can increase the numerical aperture and see the Ez component is gradually increased when you increase the numerical aperture. But for regular numerical aperture, smaller numerical aperture, you will see a dominant Ex component. We want to verify our results with a non-scattering medium with analytical solution. So we simulate the analytical solution, and also we use the Huygens-Fresnel wavelet to calculate the amplitude and phase. This is Ex, Ey, and Ez. This is the phase of Ex, Ey, and Ez. You can see this airy disk here, and you can see the amplitude is much higher for this X component. This red is much higher. Here the Ez component is not that high for a numerical aperture of 0.667. And when you increase that one, you can see this Ez component will be increased. And these are the phase relationship. And we, to compare our technique, we subtract one from the other, and we found the differences are quite small, less than 2-3 orders, depending on the number of radiating points we use on the surface. So we can reduce the number of radiating points, then this error is going to be a little bit bigger, but still it's going to be more than 3 orders of maximum amplitude. So now we can solve this problem, our problem. I got this image from JOSA last month issue. They showcase our results. So this is the technique we use. So now we have this single scatterer. We can use this Huygens-Fresnel wavelet. When this wavelet hits on the scatterer, it will generate a 3-dimensional scattered field. And from that scattered field, we can consider the scattered field going towards our detector location. We can create a grid location in our detector and consider one location and see what kind of 3D, what kind of a scattered field coming into that location. And same thing for this wavelet. it will generate this kind of a three-dimensional wave, three-dimensional field. We only calculate the scattered field going into that direction. We don't need to calculate the whole 3D field. What we do is we find the theta phi values and then use me solution to calculate the scattered field at a given distance. We use that the first set of equation, not the far field one, the other set of scattered field calculation equations, and we calculate the scattered field at that location. So what happens when we have two scatters? So in this one we continue this process for all the radiating locations. So we what happens when we have two scatterers, we can consider same thing with the plane wave solution. We consider wavelet is coming and hit on this one, it generates one scattered field, and this wavelet generates another scattered field. If we are interested in this location, we get that scattered field and then other scattered field. Same time we consider secondary scattering. So this scattered field may become an incident field on the second one and provide a scattered field on the detector. So we do the same process on this case for two scatterers. This is the way we do in a medium with spherical scatterers. Same as previous case, we uniformly sample this spherical cap and then project wavelets toward the spherical scatterer, and then during that time we advance our phase. When it reaches, we'll have a different electric field and phase at this location. Then we find the angle to our detector and a distance to our detector, and then use me solution to calculate the scattered field, and then we store that data at the detector. That's how we do for scattering medium with spherical scatterers. So we use different cases. So in one case, this is a single scatterer on the located on the optical axis, and this is off the axis. This one is off the axis, but the distance is 15 microns. This one is 6 microns. And then we use two scatterers. They are located at different depth. And this one is 6 micron, other one is 15 microns on each side of the optical axis. So these are the results, the amplitude distribution, and we compare those results with FDTD. You can see the comparison. For this one, they take like 300 process hours, but the actual time is less. These results we can get in like minutes. We can get these results in 2-3 minutes, depending on the resolution we need. We can get quicker. And the phase also can see a very good match between phase and amplitude for different size of scatterers. This is 2.5, this is 5 micron. And we can define different detector planes. That means when we want to capture different planes, we can define different detector planes. What we do is we get the scattered field at each pixel and store that one for that plane, and then we take the next one, store that data. Like this is for non-scattering medium. For that one, we get the incident field and store at different locations, and we can show this cigar-shaped profile here. And when we have a single scatterer, this is what happened to this focal volume, and it is going to be displaced, and its amplitude is going to be increase or decrease. It depends. You can do a simulation and see how this scatterers affect the focal volume. pros of this method is 2 to 4 orders of magnitude faster than FTTD. We don't need high performance computer system to do simulations. You can use laptop or regular desktop to do simulations. We don't have to propagate through entire volume as in FTTD. You don't need to solve magnetic field and electric field over and over to get into your detector location. You use Huygens-Fresnel, and so we bypass that technique, so that's why we get a speed gain. And also you can reduce the detector resolution, so you can place grid location in different spacing, and you can get a quick snapshot of electric field distortion. Then you need detail. You can increase the detector resolution, and so you can see more details. And cons are when you have thick samples, you need to populate that with scatterers, large number of scatterers. Then we may not see a huge speed gain, because for each scatterer you need to propagate those Huygens-Fresnel wavelets toward the scatterer and create scattered field, and we have to do that for all the scatterers, so we may not see a huge speed gain. And in this case we use spherical scatterers, but we need to use real biological sample scattering data to get, like, what we plan to do is next step is to use ellipsoid and cylinders, so that we can approximate certain biological tissues as cylinders and ellipsoid, and then we are going to store amplitude scattering matrix data for those things. We can calculate, we can find those information, and then we are thinking about how we use that information to model actual biological scatterers. So that's going to be a huge task. I mean, but this is like a starting step. So we go step by step, and this is solving focus beam propagation in a medium with spherical scatterers. And this is the GUI we are going to use this afternoon. So I have some parameters used for this one, and I calculated lookup tables already, and you load 3 lookup tables, and you can load them, and these are the scatterers. I use 3 scatter sizes, 1 micron, 2.5 micron, and 5 microns. So you can select the scatterer and their locations, and then you can select the plane, XZ plane or XY plane, and let's remove this one. I will leave that one for you. And then you can do a simulation. So the first one is analytical solution. The second column. So let's consider this one as first column. Second column is analytical solution. Third column is Huygens-Fresnel approach. In Huygens-Fresnel approach, we calculate the incident, scattered, and incident plus scattered. So this one is just for reference, and it's the analytical solution. So you can toggle between these radio buttons and find the scattered field and incident scattered field. And here you can see different component, EX, EY, EZ. You can select those components and see what are the amplitudes, and if you want to see log scale, you can look at log scale. If you want to zoom this one a little bit more, you can use, I can do that one. You need mouse wheel button, so you can zoom it and see what's happening in the middle. No. This. Okay. Okay. So I guess we learn focus beam distortion in scattered media and why we need focus beam computational model, rapid computational models, and we know we can do modeling using FTDD, and they are powerful tools, FTDD and Monte Carlo. They will give, FTDD will provide accurate results. It is like the gold standard to solve Maxwell's equation, the gold standard numerical solve Maxwell's equation. So we look at that one, and then we understand the concepts, equations, and principles used in focus beam propagation. After that, we learn how plane wave propagation in scattering media, and we consider single scatterer, two scatterer, and multiple scatterers. Then we look at Huygens-Fresnel principle, the principle, and how we apply those concepts in recently developed focus beam propagation model. So, thank you.
So you went over it, but I kind of missed some of it. Can you go over how to calculate the scattering matrix in a little more detail?
You mean the mean scattering? This one? Okay. And this one, calculate the scattering matrix or calculating scattering field. So the scattering field, scattering matrix. Next one. Okay. So this is calculating of amplitude scattering matrix component. This is the equation to calculate that one, and it is an infinite series. What we do is we calculate AN, BN, and then substitute those values here to calculate S1 and S2. This P and cos theta is first derivative of Legendre polynomials, and I think this whole thing is explained in Van de Haal's book and Born and Hoffman's book. They have detailed explanation how you start from spherical harmonics, then get into Riccati-Bessel function, and then do these calculations. And you can calculate this S1, S2 theta from that one. And here, I forgot to tell that this is far field S1, S2, and here we have R dependent S1, S2. That calculation is a little bit complex than this one, this S1, S2 calculation. We have more parts, more more things coming up.
When you talk about the Huygens-Fresnel principle, or can you show the picture? Yes. So I understood it when you talk about just a plane wave, where we will have, if it's a 1D plane wave of sources, there will be fringes, interference, constructed, destructed. So it's 1D fringes. And then when you move on to the focused beam, when it's a curve of lasing sources, is that going to be if it's 1D, is it going to be a curve of?
It's not 1D, it's 3D. It's a spherical cap.
Yeah.
So those radiating points are distributed on the spherical cap and start to emit from each spherical cap. So when you consider any location, and then the next, okay, this one, when you consider this location, all these Huygens-Fresnel wavelets are coming into that location from this whole 3D sphere. So they are directed in different directions. So those are vectors. When you add them, you convert them to X, Y, Z components. So they are not 1D, it's 3D. It's
yes. Okay. So
I think you have a different question. Right?
So if it's 3D, it's all coming to in phase if it's at the center point.
Okay, yeah. You can see that one. So let's get into this location where the nominal focal point is. So from this the spherical cap to that nominal focal point, that distance is the focal length. It's constant. So all these wavelets travel same distance, and so now, but they are in different, their propagation directions are different. They are not in one direction. So you need to get into XYZ components to see their directions. I mean, when you add them, you need to add them that way because vectors are directed in different direction. But their phase is going to be same phase because they travel same distance. Their phase is going to be, I think I can show, okay, here. So this one, they travel same distance, their phase is going to be same phase. So they propagate with the distance, same phase. So at that point, it provides a constructive interference. So other example is that one. You can consider the other location. This location, you can see one phase is like that, other phase is like that, towards down and towards up at this location. When you add those two phases, it's a destructive interference. So you shouldn't see anything, but practically you will see some. You'll see a certain value here because it's not zero, because when you do computer, there's a accuracy for double values, so there are some remaining parts. It's a computing thing, but in actual case it should be zero mathematically, but practically it's not never zero.
Oh, that's why you see the ring.
That's why you see the ring. So in this ring, the middle has the highest intensity, and this ring has the lowest intensity. Because you get the destructive interference from this three-dimensional Huygens-Fresnel wavelet propagation.
Isn't that also the Fourier transform of the lens? The limited aperture?
Fourier transform, you transform into different space, K space. I'm not sure about that one, the Fourier transform. Can't actually remember that.
That's why I'm a little bit confused. Like, that looks like...
So this wavelet does not mean the wavelet transform, like Fourier transform, wavelet transform. That's not the meaning of this wavelet. This wavelet means a section of a wave, part of a wave. So the section of a wave is propagating. So it's still in the spatial scale, not in a Fourier space, the state space. So we didn't transform into any space. This is a physical space. So okay, this one. So the only thing we did was we represent the lens with this kind of a spherical cap. So the lens is represented by that, and then we sample this one uniformly, and then start to radiate waves from there. That's the actual thing happening in the lens, so the wave is propagating.
Thank you.
So I'd like to know a little more about the phase, how the scattering affects the phase of the wave. So we said earlier that it's not simply the size of the scatterer, right? What else goes into determining how the phase starts and ends from the phase at the beginning of the scattering event to the phase at the end of the scattering event? What kind of stuff plays into what the difference is between those two?
So now the wave hitting on a scatterer, what happened is that it provides energy to atoms, so they are start to vibrate and create dipoles. And those dipoles generate electric field. So if there is a single dipole, like in Rayleigh scattering, then the phase is going to be almost similar to the incident phase after the scattering. But when this particle is getting bigger, you have multiple dipoles, and you get the constructive and destructive interference, which is happening inside the particle, define the phase. So there may be a phase shift, relative to the incident phase, there may be a phase shift. So you have to use mean theory or some kind of a scattering calculation to find out what is that phase, initial phase, starting from the center, because every time you take the distance, you start from the center of the particle to the distance you are interested. So you have to consider what is the phase at the center. So that one you can calculate using mean theory. It provides the S1, S2. Those are complex numbers that carry amplitude and phase. So that phase is going to be 0 or very small for Rayleigh scattering. But for me, when particle is getting bigger and bigger, this phase is going to shift relative to the incident phase. It's going to go up or down, depends.
Gotcha. Thanks.
When you were talking about primary and secondary and tertiary scattering between two particles, and you were talking about working with ellipsoids and cylinders to better model biological tissue, how would the scattering be affected if the shape of the scatter wasn't a perfect sphere like you were describing then?
So yeah, good question. I think in those cases, we have to consider, we can always, we can have different shapes, but we can consider distance from one shape to other shape at different locations. So let's say you have an ellipsoid here, and we have a spherical particle. For simplicity, it's considered this one is a spherical particle, and this one is an ellipsoid. But we can consider the distance to the top sides and every location, and we can find the minimum distance, and we can see what is the distance. So depending on the shape, orientation, we have to find where the closest point, and that point is affected first, and then the other point. So it's going to be complex. It's not simple. This is going to be really complex.
Can you still use mean theory if it's not sphere?
No. But there are some derivatives based on mean theory, but mean theory was derived for a spherical particle.
Just want to make an additional comment. So, John, can you go back to your slide that you put up in response to Matt's question about the scattering amplitude matrix?
Oh, that's fine.
So, yeah, the one following that, or before, yeah, right here. So one thing I just wanted you all to notice is that the scattering amplitude matrix on the bottom, it actually has only two elements along the diagonal. And that's because for a sphere, the parallel component of the incident electric field can only affect the parallel component of the scattered field because of symmetry, and similarly for the perpendicular component. But if you have a non-spherical particle, in fact, the interaction, even of a pure parallel incident parallel polarized wave, can give rise to scattered waves with both parallel and perpendicular polarization. So that's an additional element that adds to the complexity of that problem.
So in that case, you will have S3 and S4 there. So that means when you have a value there, these two components are going to contribute for that scattered, not only one.